Okay, we are continuing with logistic regression today, picking up where we left off. But first I'm going to start with a quick review of the dichotomous predictor within logistic regression. Now remember, anytime we're doing a logistic regression, we're predicting the probability of one, which is in your readings is sometimes referred to as the probability of success. If x and y are positively related, then there's a low probability that y will equal 1 when x is low, and a high probability y will equal 1 when x is high. And it's the opposite if they're negatively related. Now in SPSS, which is, or in R, both of them, they provide you the output for a logistic regression in 2 steps. And I pointed this out because I think it's important for you to see how logistic regression is also relying on our model comparisons approach, which we've been talking about all semester. All we're trying to do is explain error in our model. So they give you a block 0, which is a block with absolutely no predictors in it, and then they add some predictors to it and say, how much better of a job are we doing now? If you remember, a couple of other things we talked about is the intercept here is focused on when x equals 0. So any predictor in the model has to be at 0, and that's what the constant or intercept is talking about, the probability of. So it's the probability y equals 1 when x is 0 over the probability that y equals 0 when x is 0, which this is, by the way, the question that I got wrong last week on the quiz in class. So in our case that we went over yesterday, it was the probability of having tenure at Kenyon over no tenure at Kenyon College, because that was our 0. Hello. Oh, here we have the exponent b. So this is the odds ratio. And just like with the, come back. Hello. Is the odds ratio over here. So this is specifically the odds over one another. And for the slope, again, I think the exponent b, this odds ratio, is a much easier way to sort of explain what's going on within the context of your model. And in our dichotomous predictor, it was the odds. Now we're, instead of talking about the odds of yes over no, if you were a 0 on the predictor, now we're going to talk about the odds of yes when you are a 1 on this predictor, a 0 on this predictor, over the odds of yes if you're a 1 on this predictor. Again, just like we did in our standard general linear model, we're talking about a 1 unit increase in x. So a 1 unit increase in our x corresponds to what kind of odds ratio change? A change in the odds. So the same concept applies when we look at continuous predictors, only, I find that sometimes continuous predictors are much easier to understand and sometimes they're more confusing. So you all can vote at the end which one you think was a little bit more confusing than the other. With a continuous predictor, we can extend the same idea that we were using before with a dichotomous predictor to a continuous predictor. And so the example that I have in this data set is called, this data set's called smoking subset. And we're looking at whether age is related to whether or not someone is a smoker. Cigarette use, using cigarettes. Do you use cigarettes, yes or no? That's our outcome. And within SPSS, our syntax doesn't look any different. And again, because we're still on the model comparison approach, all of our analyses are going to be reported in 2 blocks. This is pretty repetitive, so I'm going to go a little bit faster than I did when I went over this with dichotomous predictors. But just to reiterate here, the research question that we are answering in this case is the probability of being a smoker related to how old the responder is? And because a lot of our work so far this year has focused on considering where the data come from, because you are the only one who can interpret it, this is a subset of like preteen to young adult people. So we have people as young as, I believe it's 12, and all the way up to like 24, 25. So we're going to hope that 12-year-olds are less likely to be smokers than older kids. Okay, so just like before, our block 0 is basically unchanged. This is the null model, this is the empty model, the model with no predictors. All of these coefficients are interpreted exactly the same way that they were before. Now, do you remember this little contingency table here? Just like before, what they're doing is using just the constant to predict whether we think each person will be a smoker or not a smoker. And essentially, this is just the mean of, remember, it's just like guessing the mean for everyone. So the mean here is how many people smoke or don't smoke. So we have more people who don't smoke than do smoke, 870 versus 220. And so this model is going to predict, this empty model is going to predict that nobody is a smoker, because that gives us the best overall probability of being right for a random person. Here we have the observed, here we have the expected. Now, just like we talked about before, the WALD is a chi-square test for the null hypothesis that the constant equals 0, and the extent to which this is not 0 suggests that will be reflected in this WALD test, significance test. So now to get a little bit more interesting, now we're in block 1 where we have included the predictor of age. So here, when we're looking at age, we'll get a lot of the same information that we've gotten before. We've got our R-squared values. R-squared are pretty useful when you're comparing values in logistic regression. Absolutely, they're not quite as useful, but still a good thing to report. So here again, we talked a little bit about each one of these models, these steps for an omnibus test of model coefficients, and this is just overall testing whether what we have entered into the model at this stage has significantly decreased our error. And a larger chi-square test here is indicating a better fit or a more decrease of error in the model. Okay, so here we are in block 1. Now we have our coefficients box, our variables in the equation box. We're going to get an effect of each predictor on the outcome. In this case, we have one predictor and the constant. Just like we talked about before, if the level of the WALD test is small, if we have a significance level or a p-value here less than 0.05, then we would consider this parameter to be statistically significantly different from 0, and it would be considered useful in our model. Now, before when we've talked about in the general linear model, when we're talking about 1 unit increase in our predictor is corresponding to this much increase in y. That's how we've been talking about these b weights. It's not quite the same here because remember, we're not fitting a straight line. We're fitting this probability S-curve. So instead, well, we'll talk about it anyway. Okay, so we've got the increase in log odds for 1 unit increase on your independent variable. And the reason that I think this is not talked about very much is that it's just kind of difficult to explain. But essentially here we'll get within the constant, the average log odds of smoking for someone who is 0 years old is -7. So again, not very interesting or helpful. But over here with the odds ratio, I find these to be much more easy to explain and interpret. So this is the odds when all predictors are 0. So it's the odds of being a smoker for someone who's 0 years old is 0.001 times that of not being a smoker. But again, because we have to think about when all of these predictors are 0, we're focused on when someone is 0 years old. You can also say it like this: respondents are 0.001 times more likely to be a smoker than not be a smoker when they are 0 years old. And that makes me think that maybe we should have centered this predictor variable because 0 years old is not a very useful metric. I would hope that nobody who's 0 would we be expecting to smoke. So, given that age is a significant predictor within this model, let's go ahead and recenter this variable so that we can get a better look at what's happening in the model at a more reasonable age besides 0. So, remembering that we're interpreting all of these when all predictors are 0, so what I'm going to do is recenter age from regular age in years to recentering it at age 18, which is when, at least in the US for a while, when this data was collected, you had to be 18 to purchase cigarettes. So if you look down here, once I've recentered age to be age at age 18, I don't see a change here for the age coefficient because my age coefficient stays the same no matter what. What I do see is a change in the odds ratio and the logit here for the constant. Because remember, when we're thinking about the constant, we're interpreting it when this predictor is 0. So when someone is 0 years old, they are 0.001 times more likely to be a smoker than not a smoker. But when they're 18, the odds ratio is pretty close to 1. In fact, it's not even statistically significantly different from 0. So this means there's no difference between the probability of being a smoker and the probability of being not a smoker when you're 18 years old in this data set. Okay, so centering changes the meaning of your constant, but not the meaning of your predictor in this case. All right, let's move on through this block to the slope. So let's talk about the slope of age. So this is representing the corresponding change in the odds for a 1-unit increase in your independent variable. And the independent variable here is age, so 1-unit increase is 1 year. So that means a person who's 1 year older, which is the same as being 1 unit higher on our IV, will have this much greater odds of having y equal 1. So the odds of smoking for a 16-year-old are 1.5 times greater than the odds of smoking when you're a 15-year-old. So this interpretation is actually really similar to how we were thinking about it in our dichotomous predictor. It's just that this is theoretically limitless within the scope of our actual observed data. Instead of only being able to do it once, you can do it a lot of times. Oh, and this is just to say that this continues up so that the odds of smoking for a 17-year-old are 1.5 times greater than that of a 16-year-old, and so on. So what's kind of cool about this is, just like we've done in the past, we can create an equation from this, and we can calculate the predicted score for each person. Do you remember how we did that in the GLM when we were learning about correlations and we calculated the mean for everyone and then we subtracted and got everybody's error? And then you can use the same thing to calculate and get everybody's predicted score on y for a particular equation. And we're going to do exactly the same thing here. So what we can do is, so first I'll show you, this is how I've harvested the parts of this equation. I don't know if you remember, yesterday I showed you what this equation looks like with nothing in it. This is sort of written in syntax terms, but you can see it's 1 over 1 plus exponential. I know it's 2 negatives, which is very confusing, but it's always exponentiated to the negative. So then I bring this negative down inside the parentheses, and then it's 0.412 times age. Okay, so I'm creating this thing. It's called a y hat, and I'm going to create it for every different age in my data set because I'm creating it for every person. And then I'm going to graph it. I'm going to use this little syntax down here, which will plot age and then age with smoking and I'll get this variable y hat in here as well. So you'll see what it looks like. So what I have here is age on this axis. Age 8. Oh, I thought it started at 10. I was wrong. It starts at 8. Age 8 all the way up to, looks like maybe 19 or so. And then I have up here, these are the smokers. These are my non-smokers. And this axis is the probability of smoking. So these are our observed data. The observed data here is this many people. It's kind of, they're on top of each other. Can you sort of see that this one's lighter and these are darker? If I could jitter them apart, you could sort of see them all. But there's a lot of people represented at each one of these. Okay, so now I have my observed data. Let's look at our predicted data. The predicted data is going to be in green, and it's based on the equation that I just harvested from that output. So this is the predicted probability of smoking based on age. And you see that down here, when a kid is about 9, it's a pretty low probability of smoking. And then as it goes up, by age 18, it's a much higher probability of smoking, using cigarettes. But it's not a straight line. You see it goes do, 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 do. And so that is what this function looks like that we're fitting to these data. It's not perfect. You see that even all the way up here at 18, it's a pretty high use of tobacco. I think that nowadays this is much, much lower in kids. But here at the time of this data was collected, it's up at here near to 80%. But it never gets all the way to 100%. Okay, so we've got all of the rules that we have used in our regression models, in our GLM models, and they're all the same kinds of ideas here that we're using in logistic regression. And just like in our GLMs, we're going to interpret the intercept or the constant when your independent variable or variables are 0. And a 1 unit change in your IV is equal to the B weight change in your DV. That's what it was before. And now we're going to do it slightly differently because it's going to be equal to a B weight change in the odds of a yes. So we can see in our previous plot, that was just basics of linear logistic regression, or one continuous variable logistic regression. And now we're going to add some more variables in because you saw there was a lot of room to grow in that model. Age is doing an okay job of predicting who's a smoker or not, but it's not great. But just like we can do in our linear models, we can also add more predictors. So in this case, what I'm going to do is add a categorical predictor, which is whether people play sports or don't play sports. My thought at the time being people who play sports might be more likely to be more health conscious and think I shouldn't be a person who smokes because I need to use my lungs for other things like running fast. So what I'm going to do here is similar to our previous SPSS syntax here. You still have the same outcome and you're still entering your variables in this other line. And just like before, we're going to get our answers in 2 blocks. So in block 0, we are again, the model is predicting that nobody smokes because it's going to be the same block 0 no matter what if our outcome is the same. Because block 0 is our empty model. Now, once I'm in block 1, what we can look at here, oh, I'm still in block 0. Never mind. I thought I was in block 1. We're just going to say, we're going to skip right to block 1 because block 0 only tells you what's not in the equation. And all of the rest of this is identical to what it was before. So now once we get to block 1 is where the results are going to be more interesting. So here we have first our omnibus test, which is testing whether this model is fitting better than a model where we just guessed the mean for everyone, essentially. The R squared here is telling me that we're explaining about 12 to 18% of the variance, depending on which one of these you want to look at. Both of these are accurate. You can report them both. You have the negative 2 log likelihood, which again we'll address in a minute. Now if I look at the classification table, which is the next part down, you'll see that this equation that we get from this result, this equation is doing a little bit better job at predicting smokers and non-smokers. You see, we've actually got some people who have crossed this cut value threshold of 0.5, and we're now predicting that some people are smokers. Now we're predicting some people who are smokers that are not smokers, but we are actually predicting some people as being smokers. Again, this table is really useful for seeing how well your equation is classifying people into the correct categories. We're not doing a great job at predicting who's a smoker. Okay, so moving on into the logistic variables in the equation, these are the coefficients that you're used to. So we're going to start with the constant, because I always like starting with the intercept. So the constant here is going to talk about when all of our predictors are 0. So that's when age is 0 and when they are not playing sports. And this is the probability of being a smoker for someone who doesn't play sports and who is 0 years old is 0.002 times the probability of not being a smoker. Now when we're going to look at sports, this is a dichotomous predictor. And just like we've done in our general linear model, we still have to think about the other predictors in the model. So you can say controlling for age. The odds of being a smoker if you are a sports player are 0.34 times the odds of being a smoker if you're not a sports player. Remember, probability of yes over probability of no. Good question. Adriana asked, do you think golfers count as sports players? Probably. So here's what I thought was interesting. Look at the direction of these odds. Are sports players more likely to be smokers or less likely to be smokers? Zero is not a sports player and 1 is yes, a sports player. So as I go from not being a sports player to being a sports player, the odds of being a smoker, the likelihood of being a smoker goes which way? I'm going to type it in the chat. Modeo, the model. So according to this model, if a person plays sports, are they more or less likely to be a smoker than if they do not play sports? We have 1 vote for less likely. Does anybody want to agree or disagree with that? I'm going to remind you that an odds ratio of 1 means that you're equally likely to have a 1 on your outcome. In this case, be a smoker. You're equally likely. I wish there was a quick way to do a poll. Unfortunately, to do a poll, I have to like go into the online system and create it. I got one agreement. Okay, let's remember here, this may help. We knew that before, as people get older, they are more likely to be a smoker. In this case, that is also the case. As you get older, your likelihood of being a smoker goes up. The log likelihood goes up. And as you get older, the odds of being a smoker go up over the odds of not being a smoker. So yes, you are correct that sports players, in this model, sports players are more likely, less likely to be smokers. The odds of being a smoker if you're a sports player are a third of the odds of not being a smoker if you're a sports player. Okay, I'm going to keep going. Look at that. I even told you here. For any, I did the inverse here. So for any given age, a non-sports player is 2.9 times more likely to be a smoker than a sports player. So it seems like controlling for age, my hypothesis was correct, that sports players want to save their lung capacity and don't want to be smokers. Oh, that's me doing the inverse. Okay, so for age, an odds ratio greater than 1 means older people are more likely to be smokers. And so you would interpret that by saying, controlling for sports status, a 1 unit increase in age, which means 1 year, corresponds to an increase in the odds of smoking by 1.5. But again, we have to put it in the context of sports status. So I did that here, controlling for sports status, but you could also do it by saying for any 2 non-sports players, the odds of smoking for someone who's 20 are 1.483, times the odds of smoking for someone who's 19. Going up changes the odds. I didn't wear my shirt. I have a never tell me the odds shirt. I'm really sad I didn't wear that. I forgot. I have to mourn that for a second, sorry. Okay. I already did some of this. Who is more likely to smoke? Someone who's older or someone who's younger? Who's more likely to smoke? Older people are more likely to smoke. That is correct. Older, because my odds ratio is greater than 1. Someone who plays sports or doesn't play sports? Someone who doesn't play sports. I already made you answer that. Okay. So, now I'm going to have you do one all yourself. Here I am predicting whether survey responders will use the internet or not use the internet. This is a survey from around 2005. So my predictors here are how old the person is, and this ranges from age 18 to age like 99. So I have age, and then I also have level of education. Level of education is, level of education is, I believe it just goes, more is up. Oh no, I have more. I have 1 is a bachelor's degree and 0 is no college degree. That's my education. I have age in years where higher equals older. And my outcome, 1 is yes, we use the internet, and 0 is no, I don't use the internet. So our outcome in this case is going to be, I'm curious who's using the internet. So here's what I want you to do. I'm going to give you about 8 minutes. That's 2 minutes per question to try to answer all 4 of these using this information and these outputs. And just like we talked about last time with number 4, I want you to describe this classification table on whether we're doing a good job predicting what's going on here. Okay, I'm going to pause the recording and I will set a timer for you. Okay, we're back. So what I'd like to have us do is go over these. It sounds like from my visits to breakout rooms that question 1 was maybe the most challenging of those questions. Would you agree, friends? Can I have a volunteer to go over what interpreting the constant, how you would interpret this constant?
I can give it a go. Stab.
Take a stab.
So the probability of not using the internet when someone is 0 years old and has no college degree is 1.76 probability of someone using the internet. There's some mumbling at the end that I was trying to like find the right words to place the last few, but that's kind of what I got for that.
So when we're talking about probabilities or the odds over here would be in the exponent b's. And
Yes.
so, and you actually have that backwards. So we're always doing
Oh,
the probability of a 1 over the probability of a 0.
I had that there and I scribbled it out because I was like, I don't think that's right, and I just literally did that. I'll
So the
re-scribble it
odds
out.
of 1 over the odds of 0. So does someone else have one that reads like that you would like to? I'd love to have somebody else's wording because there are lots of ways that you can say the same basic thing. I can roll a die and make somebody do it. Dun, 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 dun. Dice rolling. I know many of you had it. Many of you went over it with me, so I know that you can do it. Okay. 1, 2, 3, 4, 5. That's Tiffany. Can you read yours for me, Tiffany? For the group so that we can all hear it?
Oh, for the constants, right?
Mm-hmm. The
Okay.
constant.
The possibility of using the internet for someone does not have a college degree and who is 0 year old is 5.8 times the possibility of not using the internet.
Yes, exactly. So we're talking about anytime you have the constant, the probability of a 1 over the probability of a 0, or the odds of a 1 over the odds of a 0, that's the 5.8 exponent b's, the odds ratio, for people who are a 0 on all of your predictors.
I have a quick question that might be a little super basic. Is there a difference between saying is 5.864 higher for people using the internet than people who don't use the internet versus 5.86 the probability of people not using the internet?
Yes.
So I want to use the latter, right?
So the 5.86 is the odds of 1 over the odds of 0. So the odds of using the internet over the odds of not using the internet. And so that's, if we do the inverse, which we can do by doing 1 over, we can get to the opposite. If you wanted to say I'm actually not going to do that because that's just going to make it confusing. We're all in the constant. We're always talking about the odds of a 1 over an odds of a yes. Odds of a 1 or a yes over the odds of a 0 or a no. And however they have here. So here you can see that they use the internet as 0 and 1 for no and yes, because I've said that here. So who's more likely to use the internet? Someone who is older or someone who is younger? Holding education constant. Hashtag questions I should have put here in your numbers 1 through 5. As age goes up, what happens to the odds of getting a 1? They go down. So
Okay. So I'm sitting here, and that's where I'm going wild because which one? It's not which one is for which, but like the statements are so close in my brain that like pulling them apart feels hard.
yes, this is why we're going to do a lot of them. Well, we're trying to do a lot of them is because you're exactly right. These statements do feel so close together. So here, so if we're getting away from the constant is always probability of 1 over probability of 0. That's what this one is. The odds of 1 over the odds of 0 is what this one is. Now here, for age, now we're talking about 1 unit increase in age. So it's the odds of a 1 for somebody who's 18 over the odds of 1 for somebody who's 17. That's what this one is. The odds for someone who's 65 over the odds for someone who's 64. So a 1 unit, you could think about it in odds here where an odds of 1 is equal. But if you want to think about it in terms of probability or likelihood, this is as age goes up, the general probability or the general likelihood is decreasing.
In typical articles, when that's reported, do people just select an age that is most relevant to the study, or do they say as age decreases or increases by 1 unit?
Typically they would, I think it depends on the article, honestly, which is a not very fun answer. But typically what people are most interested in is the age coefficient and don't often worry about centering. Sometimes they do, but not always. So they're really more interested in, as age goes up, what happens to my probability of using the internet? In this case, the probability is going down. Older people are less likely to use the internet than younger people.
So then, am I misreading things? But like, if we compare that XP column versus that B column, if that XP column is less than 1, that means it's a fraction of, y equals 1, then the B column by default is going to be negative because it's less than 1.
Yes,
Okay.
that is exactly right. It will always be like that. And if this is if this is positive, then this will always be greater than 1.
So if it was 1, it would be 0 over in the B?
Correct.
Cool.
So let's use that information to say, for everyone of the same age 0, who's more likely to use the internet? People with a college degree or people who do not have that college degree? People who have the college degree. Because here we go. As you go up, this is positive, not negative, so our likelihood's going up. And the odds of with a college degree, of a yes using the internet with a college degree, are 1.8 times the odds without a college degree. 1-0. Oh yeah. How about the classification table? Did anybody have any fun takeaways from that? Like, did it seem like we did a better job this time than last time? Or any questions on the classification table as you look at it and how useful it can be?
In our group, we had, well, in our group, 2 people thought that it was a prediction because the 92 was really high, 52 was better than previous tables. But I was just like, well, that 52 is pretty not great. So looking at these numbers, I wouldn't know which one to prioritize.
There's no right answer, unfortunately. The key thing that I want you to take away is that you understand what those numbers mean, because that is exactly what I would expect you to put in a results section. That's exactly what I would expect you to interpret this, is to say, yeah, we did a great job at predicting who does use the internet, but we did not do a great job at predicting who does not. So depending on what you want this model to do, it could either be really, really effective or really, really not effective. I considered changing all of these examples to have to do with COVID-19 and decided that was a little too close to home and I couldn't handle it. But imagine that you have a PCR test and these are the numbers on that test, the rapid test maybe that you take at home. If it's super accurate at predicting when you do have it and not very accurate at predicting when you don't, that's probably pretty good. That would be great. If the opposite was true and only half of the time that you have it, it's getting it right, that's probably not great. So depending on the goals of your assessment or your prediction that you're trying to do, it depends on which one of these numbers you would want to maximize. It's impossible just about to get them both very high. Thank you for sharing that, because I think that's really important to understanding the goal of why I'm showing you this stuff, is so that you understand where the numbers, what the numbers mean, so you can talk about them when you see them in your predictions. Okay, here's what I want to do to push this point home a little bit more. My time estimate was a little bit off, I'm sorry. But what I want to do is I want to show you just a little bit more about how these work. Now there's a ton of slides here, but I'm going to just show you a little bit about one of them, and then I'm going to leave the rest for you to look at through if you want to. Okay, so I've just taken the equation and I have gotten everybody's predicted scores here. So what I've done is I've taken some plausible values for sports 0 and 1, 0, 1, 0, 1, 0, 1. For plausible ages, here's 2 people who are 13, 2 people who are 14, 2 people who are 15, and so on. Now remember, what we looked at in our results before is that the odds of being a smoker are 0.27 times the odds of not being a smoker. That's what our odds ratio is here. And now here, the predicted logit is 0. So here the odds are 0.5. Or the odds ratio is 1. The probability is 0.5 and the logits are 0. So this is where the B, I think, who is it that said this? Hannah, did you say this? That if the logit is 0, then our odds ratio would be 1. So you could see this sort of play out across these expected scores. Anytime I have a negative logit, that would be the B, I would have an odds ratio that's less than 1. And when I have a positive logit, I have an odds ratio that's above 1. So odds ratios are multiplicative. So if I'm going to look at 2 people, remember here's age 13 and age 14 for 2 people who both don't do sports. Here's the odds ratio. As I change by going up by 1 year, my non-sports player who's 13 has an odds of 0.27, and my non-sports player who's 14 has an odds of 0.40. So this odds, 0.40, is 1.48 times the odds when they were 13. So 0.27 times 1.48, this was our coefficient from our model, 1.48, results in 0.40. I just show you this to show you how this math plays out in terms of our prediction. It goes up by 1.48, but it's going to do it again as I go from age 14 to age 15. As I go from 14 to 15, it goes up again, but instead of going up by just the same number, which is what we were able to do before when we were fitting straight lines in the general linear model, these are exponential, so they're going to increase more as you go up. So this is times 1.48 times 1.48. We have to do it twice to go up to 0.60. Okay, I just wanted to show you how this sort of works. And you can play with this if you want to see how the log odds, the logits, and the odds ratios change as you move through all of these predictions. That's pretty cool. Okay, now, the last thing I want to talk about is deviance testing, which is the whole idea of determining whether your model fits better now than it did before. And what we're going to do that is use this -2 log likelihood. So we're going to compare the difference in log likelihood values between our empty model and our full model. And all we do is take this -2 log likelihood value when age is this is one where I'm comparing our model with age as the only predictor and one that has both age and sports. And we're just going to do they call it a deviance test. Why do they call it a deviance test? Because we're taking the difference between these two. So you're looking at how much better this fits based on how our log likelihood, based on our log likelihood number. And then we look at the differences in our degrees of freedom. And we get the degrees of freedom from our other table here. With age only, we have 1 degree of freedom. With age and sports, we have 2 degrees of freedom. And so the difference between that is 1. So we would just look up a chi-squared test in the back of a book or in an Excel table to determine whether we've done a good job at explaining more variance in the model with this deviance test. So you could say degrees of freedom is 1, and our deviance log likelihood is 48. And then you can use Excel to tell you whether this is a statistically significant amount of variance we've explained. That is all I wanted to tell you about the deviance test, and I should stop waiting until the end and just start telling you right when I introduce the deviance test earlier in the model. So it's just a good estimate of whether you've done a good job explaining what's in your model. So even if your R squared is pretty small, you might still be explaining statistically more of the variance than you were before. Okay, hold on. Wait, don't look at that. All right, that is my logistic regression overview we did dichotomous yesterday, we did continuous predictor today, and 2 predictors today.